Stat students, we're going to get started on section 8.4, which is a z-test for a proportion. So we have done our hypothesis testing with mu, right? All of our hypotheses are mu equals and then mu with an inequality. Well, now we're going to go to proportions. So we're looking at percentages or proportions of things. So we're going to be dealing with p's and p-hats, as you can see from our little side symbol box. So you need to think back in time a little bit to binomial distributions. That was back in chapter 5. Because remember, binomial distributions, the biggest part about these is they have two outcomes, a success or a failure. Remember, our p does not change from trial to trial. And we also had a couple other characteristics of binomial distributions. Our trials are independent, and we have a fixed number of trials. So I didn't write those ones down, but these, I want to remind you about our two outcomes, our P and our Q, as well as our probability of success not changing. So when we calculated our mean in a binomial distribution, our mu was equal to n times p. Our standard deviation is the square root of n times p times q. We have to have a condition. A condition, it's just a little check step at the beginning. We want to verify that our n times p is greater than or equal to 5, as well as our n times q. So that's just a condition. It allows for independence. It's kind of one of those background things, but this is just a check step. We would do that even before our first step of hypothesis testing. And next up is the big part. When we go to do our test statistic, we need to know our formula for, so our formula for our p proportion, we use z equals p hat minus p all over the giant square root of p times q over n. I don't know if you like what that looks like. I always write it as p hat minus p. I don't know if that looks any better to you, but whichever way you like. And I didn't go through all our 5 steps. We know our 5 steps of hypothesis testing. We start out with identifying our claim and writing our hypotheses. We calculate our test statistic. We find our p-value by going to our table. In this case, it's going to be the z table. I'm going to just jot that down if you have room. We know we use the z table because we are calculating the z-test statistic. Step 4, we make our decision by comparing our p to alpha. And step 5, we write ourselves a summary statement using the context of the problem. So let's go over here to our symbols. So p hat, remember, is our sample proportion. If we need to calculate it, we do our x over n. X is the number of items that are what we're looking for, are favorable. N is our sample size or our possible. P itself is our population proportion. Just like in our last 2 sections, I'm going to probably tell you, I think that I'm going to say, based on a study, the population proportion of people who believe in aliens is 47%. That's what we're going to use in our hypotheses. Q, notice it's not a Q hat, it's a Q. So we're just going to do 1 minus P. And notice in our formula, we only have the P hat for that numerator. In the denominator, we're using the population proportion, and then our Q, our 1 minus P. N we know is sample size, and of course, degrees of freedom. I don't think we need to know degrees of freedom in this section, but you remember them anyway. All right, so again, I didn't go through our 5 steps. I just jumped right into an example problem. So let's just do this, and we can refresh our memories as we go. The only thing that changes right now is our formula for our test statistic. So, and our hypotheses have a p instead of a mu. So for example, sugary diets. A dietitian claims that 60% of people avoid sugar in their diets. The dietitian randomly selected 200 people and found that 128 people stated that they were avoiding sugar. At the alpha equals 0.05 level, is there enough evidence to reject the dietitian's claim? So let's start off with let's start off over here. I'm going to put all my info on the side. So this is our P. So P is equal to, and I always go to the decimal, 0.60. Our P hat is from our sample, right? So our sample, dietitian randomly selected 200 and found 128 that were doing what they were asking about. So 128 out of 200. If I gave you a percentage, that P hat is already calculated. So I would just jot down that percentage. This one I have to calculate. Sample size N is 200. And our Q is coming from our P, so 1 minus 0.6. So our Q is 0.4 or 40%. Not from our P hat. So remember that. That one's a little sneaky one. So step 1, let's jot down our hypotheses. So H sub O and H sub 1 identify our claim. So our H sub O is already given to us. It is that big population piece of data. So P is equal to 0.60. And the dietitian is claiming that 60% of people avoid sugar. It's not saying that it's less than or greater than. So the dietitian is actually claiming H sub O. We don't know bigger or smaller, so we're just going to say that our H sub 1 is that 60% of people are not avoiding sugar in their diet. It's just not. All right, so step 2, calculate our test statistic. So again, P hat minus P over the giant square root of PQ over N, just in case you needed that refresher. So my P hat is 0.64 minus my population proportion, and then I'm going to reuse that 0.6 times my Q all over my sample size of 200. Take a pause and calculate this and verify that you end up with a 1.15. Again, sometimes getting the calculator to cooperate is more difficult than setting up the problem. So I end up with a 1.15 for my Z test statistic. So again, I'm going to my Z table, and I'm actually looking for 1.15. So I'm going to go on the positive side, down to 1.1, across to 0.05, and I get a 0.8749. That number seems pretty high, right? So if I'm thinking about this, here's my mu of, here's my P of 0.6 in the middle, and I think that my alphas are over here. Since it's two-tailed, I'm going to remember to divide my alpha by 2, so I'd have myself a 0.025 because my alpha was 0.05. Alpha over 2 equals 0.025. 0.64 is over here. I don't know how far away. I just know that it's on the right side of that proportion of that 0.6. So because it's on the right-hand side, just like we did with the other stuff, I'm going to subtract that from 1. So anytime I get a positive z-score, I'm going to end up subtracting that area from 1. So that means that my P is equal to 1 minus that 8749, or a 1251. So then I'm going to go ahead and I'm going to compare my P to my alpha over 2, remember, because it is a two-tailed test. So how does a 1251 compare to my 0.025? That is definitely, P is much larger than alpha. So if I'm thinking about that, and I was going to put that p-value on here, if I've just got 0.025 and I'm going to color in a 0.1251, that is much larger than my alpha area, which means it flows into the do not reject H sub O region. Remember, I only mention H sub O. I never support H sub 1. I only reject or don't reject H sub O. So, since my claim was H sub 0 this time, and I didn't reject it, the best that I can say is that there is not enough evidence to reject the claim. Right? That makes sense. I didn't reject H sub O and my claim was H sub O. There's not enough evidence to reject H sub O, to reject the claim that 60% of people avoid sugar in their diets. I go right back to the statement. I try to pick the words right out of the original problem. Sugar in their diets. And we have completed our first z-test for a proportion. So let's do one more. I've got one more. And I wanted to make sure we did a two-tailed to remind you we still do alpha over 2 to compare to our p-value. And let's talk about a survey by Men's Health magazine that stated that 19% of men said they use exercise to reduce stress. Use alpha equals 0.02. A random sample of 100 men was selected, and 12 say that they exercise to reduce stress. Is it reasonable to generalize the results to all adult Americans? So I'm going to start over here. First of all, the magazine states that the population proportion is 19%. Our alpha is 0.02. A random sample of 100 men was selected, and 12 say that they exercise to reduce stress. So my p-hat is going to be 0.12 or 12 out of 100. And I'm also going to need my q, which is 1 minus the 0.19. So that would be like a 0.81 for my q. All right, so let's start with our hypotheses. This one's interesting. I think our claim is H sub 1 or H sub O again. So H sub O, remember, we've already got that over here. Our P is equal to a 0.19 or a 19%. And there's nothing saying that it's right-tailed, left-tailed. It just says, is it reasonable to generalize? So do we think that this is true? Are we going to generalize that 19% to all people based on our sample data as our help? So that means I'm just going to do a two-tailed test here. Z-tests for proportions aren't always two-tailed. These two just happen to be. So step 2, I'm going to calculate my test statistic. I'm not going to write down that formula again, but I'm going to remember that it's p-hat. So 0.12 minus p. Again, remember, I mentioned it before, our second value in our test statistic is always our population value. And that's going to all be over a 0.19 times a 0.81 all over my sample size of 100. When I did that math, I ended up with a negative 1.78. So this time in our two-tailed test, our p of 0.19, it is two-tailed. So here are my two alpha over 2s. Alpha over 2. Well, if alpha is equal to 0.02, this has to be 0.01. Okay, see I write in yellow. So this one, alpha over 2, is a 0.01. So this time, if I'm just thinking about where this lands, 12% is obviously somewhere down here. So it's on to the left. So when I go to find my p-value, basically I'm asking if that falls within that shaded region or not. So I don't have to subtract from 1 this time because I don't have, I have a negative z value. So I'm going to go to my z table and look up a negative 1.78. No need to subtract again. So I just end up with a p equaling 0.0375. So if I compare my p to my alpha over 2, my p-value is 0.0375. My alpha over 2 is 0.01. This p-value is definitely greater, which means I am going to not reject. I wish that I had changed this problem, because what would have happened if my alpha over 2 value was a 0.05? So if I was going to compare a p of 0.0375 to a 0.05, let's say my alpha was 0.1, then my p would definitely be smaller. I wish I had made 1 where we rejected h sub o and 1 that we didn't. So if I changed this, if I changed my alpha value, this one would have been a reject h sub o. So just side note, remember, changing the alpha changes our decision. It also changes, remember, the probability of making a type 1 error where h sub o is true, but we reject it. So let's see, step 5, we didn't reject. Our claim was h sub o, which means we've got exactly the same statement. There's not enough evidence to reject the claim that adult American men use exercise to reduce stress. That one was a little harder to get my statement. I'm not going to rewrite that statement for the sake of time, and also for the repetition of it, because we've already done it. This would be, again, if I changed my alpha to a 0.1, or if I wanted to be 90% confident. I wish I had changed that problem in the notes for us, but I didn't. So that is it for z-tests for proportions. We'll do some more practicing and make sure that everybody's good. And have a great day.